So in previous videos, we first learned about linear functions, then we learned about quadratic functions, and now we're moving on to general polynomial functions. And a polynomial is just whenever you have powers of x and multiplying and adding numbers and nothing else. So you can't divide by x, you can't have like square root x or anything like that. So as long as you just have powers of x, positive powers of x, and numbers with no dividing by x's, you are good to go to be a polynomial. Now, the highest power of x you have, that's going to be called the degree. And so that means that when I had mx plus b, the linear there, that was a degree of 1. And then I went to ax squared plus bx plus c. Those were quadratic. And that was degree of 2 because of the x squared. And now we can have any degree we want to. We could have degree 17. I will say, when you get a higher degree, the problem gets harder and harder, and we'll usually only stick to maybe degree 3 or 4, rarely degree 5. It's just something that it gets to be too long and tedious, and it's not really worth it anymore as an example for a class. On the other hand, there are definitely problems in applications, science, engineering, where you might have a higher degree and you have to deal with it. So just know that what we're doing here is the same basis for it, and you will do the same steps, it's just longer. Now, when we are going to deal with polynomial functions, the primary purpose for that right now is so that we can draw a graph of it. And there are going to be several things that we're going to need to take into account when drawing a graph. First things first, we're going to want to find our y-intercept. That's the easy part. All you do is plug in 0, and we get a y-intercept here of 0, 0. We would also like to know any x-intercepts, and for that we take our function and we're going to set it equal to 0, and then we factor things here, and you're going to get 3 values for x here, 0, -2, and +2. Those are going to be our 3 x-intercepts, if I want to write it down in point format. And then there's going to be kind of one main last thing you need to talk about. This is something called end behavior. Basically, you want to see what happens on your graph as you get really, really big values of x. So everything on the really far right of the graph and everything on the really far left of the graph, that's what we're kind of looking for here. And so what are we going to see here? Well, turns out there's 4 possibilities. The first thing you need to do is you need to look at whether your degree is going to be even or odd. And I will look at degree even for my first 2 things here. Well, if your degree is even, then either both the left and the right are both going to go upwards on the far edges all the way to infinity, or they're both going to go downwards all the way to negative infinity. And the way you know which one's which is whether your first coefficient, which we call an, if that's positive or if that's negative. Now second here, we need, if the degree is odd, and that's actually the case that we have in this problem because my degree is 3 here. Well, in the odd degree case, you either go down on the left and up on the right, or vice versa. Again, depending on whether the leading coefficient is positive or it's negative. So in this case here, my biggest term is x cubed, and the number in front of that is +1. And so that means that we are in this scenario here. That means my graph is going to go up to the right and down to the left eventually. Then we're going to plug in any x or y intercepts that we have. And then we're going to get to each point here. And there's one last step, and that is something called multiplicities. Now, I have seen a lot of students that skip over the idea of multiplicities, and to be fair, you can find alternate ways to do it without talking about multiplicities. But it turns out multiplicities, they really give a lot of helpful information, and they let you save a lot of time if you understand them. So multiplicities are going to be whenever you have an x-intercept, so in this case x is 0, x is negative 2, and x is positive 2. We have 3 x-intercepts here. And then once you have your x-intercept, the multiplicity is going to be, when you factored it out, what number was in the power. So when I factored these things out here, I look to see what number are in the exponent on the outside of parentheses. In this particular case, my multiplicities are all 1. Now, in the next example, we're going to see one with different multiplicities, so you can see how that will vary there. But for right now, they're all multiplicity 1. And anytime you have an odd multiplicity, maybe I'll put it on the top here, odd multiplicity, you go through. Whereas if you have an even multiplicity, turn around. So the idea is you're drawing your graph here, going along, la la la, and then you get to your x-intercept. If it's an odd multiplicity, you go through. If it had been an even multiplicity, I would have turned around and not gone through. However, once I go through, I still have to get to the next x-intercept, so I have to turn around at some point in time. And then at x equal to 0, again I have an odd multiplicity, I go through. At some point in time, I have to come back to the last x-intercept. The multiplicity is odd again, so I go through. And this is going to be my rough graph. This is what we're dealing with here. Now, I will give you kind of an interesting kind of point of view on these problems that you may or may not like. But if you think about it, the bigger the multiplicities you have, the worse the problem is going to be, the more factoring is going to be involved. So this right here wasn't too bad to factor, but I only had multiplicity 1s. If I had something with a really high multiplicity, it would be a nightmare to actually try to factor it. But what we can do, if I want to see if you understand those types of problems, I can give you one, the second example here, where it's already been factored for you. So you save the time on factoring, but then you have to deal with multiplicities that are other than just 1. Okay, so let's try a few things here. Let's try the y-intercept. This one's going to be a little bit harder this time because it's in factored format. Running out of room here. And if I go ahead and plug in 0 into that, I'd have negative, and then negative 8 when you cube negative 2, and then 1, and then negative 5. And then if we multiply these things all together here, it looks like I get negative 40 here. So my y-intercept is down at negative 40. The x-intercept, this one's actually going to be easier now because it's already been factored for us. So I can just solve each part separately. And I get 2, negative 1, and 5. And I can right away say what the multiplicities are for each one of them. The multiplicity for 2 is that number 3 there, because again, 2 came from this, and the exponent there is 3. The multiplicity of negative 1 is 2, and the multiplicity of 5 is 1. So those are our 3 multiplicities there. Then the third thing we want to take into account is the end behavior here. Now we need to know what my degree is and my leading coefficient. Well, we do see there's a negative 1 in front, so the leading coefficient is negative, but you might have a hard time finding your degree here because it's in factored format. So just think about this. We have x and it's going to be cubed, so x cubed, and then 2 more x's, x to the 5, and then 1 more x to the 6, so it's going to be something like a negative x to the 6 here from the negative in front. So we know end behavior when you have an even degree and a negative front is both sides down. So I can go ahead and put my end behavior in there. I have my y-intercept of 0, negative 40. Now notice I absolutely did not count down 40 hash marks there. I just put a dot and label it. So we're not really worrying about the scale of our graph right now. And then we have x-intercepts over here at 2 and negative 1 and 5. And then we see we're going in here, come to this negative 1. At negative 1, I have a multiplicity of 2. That means I do not go through, I turn around, come down to the y-intercept, get back over here to 1. At 1, sorry, 2 there. It's like a 1, but it's a 2 there. I have multiplicity of 3, which means I go through. And then 5 is going to go through. And yes, this is a bit of a mess here. I'm sure you can do a better job than I did in making it look nice there. But when I'm grading these, I'm looking for the following things. I'm looking, do you have the y-intercept either positive or negative correctly? Do you have the right x-intercepts marked? Do you have the right end behavior? And do you use the right multiplicity behavior at each intercept? So either you go through or you turn around. As long as all of those things are correct, your picture doesn't have to look too amazing for it. So this is how we try to graph a polynomial.